The next type of star that we need to look at that basically helped us to understand more about what's happening outside our own galaxy are Cepheid variables. Now, these stars are extremely luminous stars, but it's not just their luminosity or the fact that they are extremely luminous that's important. It's the fact that that luminosity varies periodically. So what we mean by that is that the luminosity is not constant. It increases and decreases over time. And important to note here as well that it's not a sinusoidal variation in luminosity. As we can see from this graph, the brightening occurs over a shorter duration than the dimming. So it's not an even pattern, and we'll talk about why that is as we go through this video. So brightening occurs over a shorter duration than dimming. And the important thing though is that we do get that predictable variation in the brightness. So by having that variation, we're able to then determine a few different things. And that was basically discovered, or the relationship that's important here was discovered in 1908 by a scientist, Henrietta Leavitt. Now the names here aren't important, but just mentioning it just for posterity. So Henrietta Leavitt discovered that there was a relationship that was linear, more to the point. So a linear relationship between the relative luminosity, and what we mean by relative luminosity is the luminosity compared to our sun. So the relative luminosity and the period of the brightening and dimming. So the reason why that was important is because it allowed the measurement of the period, which is fairly easy to measure. If you're looking at the luminosity, you sort of measure it over however long it takes. In the case of this graph above, 5.4 days. So the measurement of period allowed the luminosity to be determined. So that then made it much easier to determine the luminosity without having to figure out any other properties, and so we could then figure out that luminosity. And taking that a step further, if we then were able to measure the brightness, or the apparent brightness I should say, so measuring the apparent brightness, the distance to that star could be determined. So this allowed us to, like I said, to explore further than our own galaxy, and sort of expanded the distances that we were talking about with these other galaxies. So the reason that we can do that is by using the equation that we saw in the previous subtopic, the apparent brightness being equal to the luminosity over 4 pi d squared, where d is the distance to the star. So if we know L and B, then we can figure out what d is. And the important thing here too, as I said, is that this particular relationship allows us to extend stellar distances greater than what stellar parallax can measure. So Cepheid variable is particularly important in that sense. Now, the other thing that we need to have a look at here is the reason why we get this variation in intensity for Cepheid variables. And to do that, we'll use a diagram here. You can see the cycle that we've got going on here, and I'll just notate what's happening in each case. So if we start off at position 1, what really happens here, eventually we get a loss of hydrostatic equilibrium. So that means that the the pressure inside the star is no longer able to overcome the gravitational forces, and so the outer layers of gas will start to collapse inwards. So they collapse due to gravity. So we get the outer layers there starting to fall inwards towards the middle of the star. So that then has a fairly significant effect. So, and the reason why we get that the loss of hydrostatic equilibrium is basically that fuel sources get used up. We then go on to the second step. That means that the layer of gas there becomes compressed, and if we have a greater compression, that then means that it's also going to be less transparent. So by less transparent we mean that any of the electromagnetic radiation that's being radiated from inside the star is not going to be able to escape all the way outside the star, because that particular layer is now the radiation is being absorbed by it. In the third stage, because we have that increase in the layers being compressed, the temperature in the layer then increases. And with an increasing temperature, we also see a building up of pressure as well. So you can see now that as pressure starts to increase, then all of that gas that has been compressed is then going to be pushed outwards, and that's what we see in step 4. And after that layer is pushed outwards, that means that the gas is then starting to expand again. So in step 5, we see that the layer then cools as it expands. And as it's cooling, and it becomes less dense. And with that last step then, step 6, with a decrease in density, radiation can now escape again as the pressure decreases. And then we end up back at the start, where with that decrease in pressure we end up with a loss of hydrostatic equilibrium, and so the cycle repeats. Now if you think about this process, where down the bottom here in step 6, where the radiation can now escape, that means that there is more light that can escape from the star, and so the intensity will increase here, but then as the layer starts to get compressed going through here, we see that the becomes less transparent, and so slowly over time that layer will cause the star to dim, and then you can see as it comes around to steps 4, 5 and 6, that expansion happens fairly quickly, and so the brightness increases pretty quickly as well. So there's Cepheid variables. Two important things there: the fact that they can allow us to measure greater distances than stellar parallax, and then also the way that the variation in the luminosity of the star occurs.